Okay, so Raghu is going to start the afternoon session and tell us about black hole information. So thank you, Raghu.
Okay, thanks. The organizers asked me to give some lectures as introduction to the black hole information problem. So that's what we are going to just do today. It's just going to be old stuff. And maybe in the lectures 2 and 3, we will cover these more recent developments about islands and replica wormholes. So today is just going to be a setup of what the black hole information problem is. So a very important point about black holes is that they are thermal objects. So we are first going to start by studying some properties of thermal correlation functions. But before we start, I wanted to list these 4 references that I think are not, well, apart from number 3, are maybe not that well known. But for students, for example, this reference 1 contains a lot of detailed calculations about 2-point functions and the expectation values of stress tensors just for Rindler space, for example. So, many times you don't find that many calculations written down, but like this paper is like a review, but it has a lot of detailed calculations. The second paper is a derivation of Hawking radiation that I really like because it focuses on correlation functions rather than just describing some state, the underlying state. So this is a paper by Friedenhagen and Haag from this Communications of Mathematical Physics. These Lesuch lectures by Strominger focus on 2D models. And the advantage of 2D models is that the stress tensor on the evaporating black hole geometry can be completely determined using the trace anomaly and things like that. So this makes it very explicit, and it's also possible to solve for the back reaction and things like that, and really see the black hole horizon shrink in time. So, and this last one is a really, I think, impressive paper by Don Page and his collaborators, in which they try to solve for how the 4D Schwarzschild black hole would shrink as it evaporates. So they need to know, for example, the outgoing flux of Hawking radiation and the stress tensor. So these are some useful references. So you can read them. I won't be covering too much of either one. I just thought it's useful to present these. Okay, so let's start by discussing thermal correlation functions. So here I have written beta is a real number. It will stand for the inverse temperature, so it's positive. And I would like to define this subset of the complex plane, which is this strip here. So it's a strip which is defined by the fact that the imaginary part of the complex number should lie between 0 and negative beta here. Okay, and then you have some quantum system with some Hamiltonian. Doesn't really matter what it is, it's a quantum mechanics or a field theory or whatever. But let's say in it, there is a scalar operator phi. It's Hermitian, let's take it to be Hermitian. And let's say H is the Hamiltonian of this system, which is bounded below. Its spectrum is bounded below. So we define for all t in this strip, so t is a complex number, you define this g of t as 1 over z. Z is the thermal partition function, is trace of e to the minus beta h. So you insert this state, and then you have e power iht phi e to the power minus iht phi. So if you want, you can think of this as the operator phi of t. Okay, but I just want to emphasize that I'm just taking t to be complex to start with. So it's not real or imaginary or anything, it's just a complex number. Okay, so we have these 2 exponentials here. There is this exponential and this exponential. So we have defined this object, g of t. It's a 2-point correlation function, but I've chosen to write out these exponentials out explicitly. Okay, so there are 2 exponentials and there's a trace here. So we would like both of these exponentials to converge. That means if we insert a complete sum of states, these exponentials should have negative real part. So if we look at the first exponential, you have a negative beta plus it. So you split t into its real part and imaginary part, and you see that you get this combination beta plus mt. So this quantity should be positive for this trace to converge. And similarly, if you look at the second exponential, you have a negative it. So that again, you split into its real part and imaginary part. So you see that the imaginary part of t should be negative in order for this exponential to converge. So if you put both of those conditions together, you get that mt has to lie between these 2 regions. So that is the reason for picking this strip S, because the function g of t is analytic in this strip as an open set. So note that I've omitted the boundaries. Okay, so the usual, for example, Weitman function with one ordering would be the boundary value of this analytic function as you approach the top line of the strip. And the Weitman function with the other ordering would be, if you approach the lower boundary. Anyway, those remarks are not important. Okay, now another very important property of G is the following, that if you take 2 points, T1 and T2 in this strip, whose midpoint is the midpoint of the strip. So M is the midpoint of the strip, which has a complex coordinate negative I beta over 2. Then the G evaluated at those 2 points is the same. So it's a simple exercise to show this starting from just this definition. So you just replace, check T1 and T2. At some point, you need to use the cyclicity of the trace. So this property is very important. It's called the KMS property. And at some point, you'll also have to use the fact that we picked identical operators, real operators. Okay, so a specific case of this is if you take tau to be a real number between 0 and beta, and you just ask for the values of the function along this purely imaginary line. Then if you just apply this inequality, it will say that G of negative I tau, so that's some point here, will be equal to the corresponding value at negative I beta minus t, such that again, M is the midpoint of these 2 points. So what is the meaning of this inequality is some physical picture. So as we know, thermal partition functions are evaluated if you're in purely Euclidean signature, that there's a circle of circumference beta. And in this configuration, that's this circle. So when you go from this point to this point here, so that has circumference beta, and we have inserted two operators here. So as you can see, like there's a symmetry between tau and beta minus tau in this figure. So that is this statement. If you chose tau to be purely on this line segment here. So why am I emphasizing this? Is because there's actually a converse to this, that if all correlators in your theory obey this KMS property, then the state must be thermal. So there's also a converse. So if all operators obey this property, then the state has to be thermal. And actually this is a very nice way to diagnose thermality of states, so which is what we will get to now. So the most simplest example where we see some kind of thermal physics in the context of QFT and the information problem and so on and so forth is just to consider Rindler space. What is Rindler space? Rindler space is just an open subset of Minkowski space. So we define it like this. So let x0 to xd minus 1 be just standard coordinates in a d-dimensional Minkowski space. And let x vector denote the d minus 2 tuple starting from x2 up to the last coordinate xd minus 1. So we look at now the x0, x1 plane and look at this open set here, which is to the right of these lines. So that's the equation here. So let's call this R plus. It has x1 bigger than the absolute value of x0. So you define new coordinates, xi and eta, by the following relations. x0 is xi sinh eta, and x1 is xi cos eta. Xi is positive, so it goes from 0 to infinity, and eta goes from minus infinity to infinity. So what does this pictorially look like? This line here is a line of constant xi. And eta starts at minus infinity, sorry, it should asymptote to this thing. So eta starts at minus infinity here, comes to 0 here, and then goes to plus infinity. And the lines of constant eta are just straight lines, like that. So this is some constant eta negative, this is eta 0, and this is eta positive. So this is what this coordinate system looks like. And the point is that it only covers a subset, an open set of the Minkowski space, which is called R plus. Okay, so the second exercise is that if you now take this world line that I drew here, this yellow world line, which is a line with fixed xi and x vector, and only eta is changing along it, then this trajectory has constant proper acceleration. Okay, so this is an exercise. So now what does this tell us? So imagine just three-dimensional Minkowski space. So there's a third direction x2 here. So imagine this line of where just x2 is varying. And if you have other coordinates, they will x2, x3, x4, etc. You just fix them to be constant something, right? So that is in space, it's a codimension 1 object. It's a hyperplane in just purely in space, right? So that's like an infinite flat object, like an infinitely flat planet, which is spanned by those d-2 coordinates. And this object, if you just think purely in space, forget about the time, it's moving perpendicular to itself, like in this x1 direction, at a constant acceleration. The acceleration is constant because of this. So what this does is this setup mimics a constant g on an infinite flat planet. And because accelerations and forces of gravity are somewhat similar, this is perhaps the simplest setup where some kind of gravitational effects are visible. So I just wanted to give this interpretation of Rindler space. Okay. Is there any questions till now? Is the geometry, yeah.
While writing out the K-means condition, you didn't take the tau to be normal, right? Take 0 and beta values.
Well, no, because you see, if tau is 0, then these two operators are on top of each other. And usually, like if they are coincident, like they are singularities. So actually, there will be, usually this function, this g of t, will not be definable on the boundaries of the strip, except perhaps as a distribution. So those are like the Weitmann functions, like usually these boundary values are distributions. So how many, we have d coordinates, one of them is time, right? So the space is d-1 dimension. So just imagine this 3-dimensional space. So we have x2 and x3, let's say the floor of this room is spanned by x2 and x3, and x1 is perpendicular to it. So what is this motion of this yellow line, right? This yellow line is moving in x1, right? So we have this plane and it's moving in x1 direction, and it's at rest at this time, and then it's constantly accelerating. So it will approach the speed of light here, and similarly in the past. So it's like a, so imagine there was an actual object there that was moving with this profile. So that's what it would be, that's all I'm saying. And why is this important? Because like when you first start doing physics, you solve problems in which you have a constant g vector force, right? Like at 9.8 meters per second square. So this basically is that setup, but in relativistic gravity, like a relativistic physics. Because acceleration in GR is supposed to be somewhat similar to force of gravity. Just at an intuitive level, not. Okay. All right, so now let's just get into the actual, what did these two things have to do with each other. So now we consider CFT, it's just a conformal field theory on this Minkowski space. And we put this CFT in its vacuum state, a vacuum state of the Minkowski space. So that is some well-defined state. And we take a scalar operator with scaling dimension delta in this CFT. Okay, so phi is the scaling operator. And I want to calculate its 2-point function, where the 2 points are here A and B. So again, I have taken this yellow line, and I just want to calculate phi of B, phi of A. Okay, so since it's a scalar operator in a CFT, we just know the answer, right? We can just write it down. So it will be T2 minus T1 square plus X2 minus X1 square plus X vector 2 minus X vector 1 squared to the negative delta, right? Just by scaling properties of a scalar operator in a CFT, this is the 2-point function. So I now want to convert this from this t and x coordinates to xi and eta, okay? So t is, by the way, x0. So I defined here t to be x0. I didn't want to write it with a subscript, but that's what it is, okay? Okay. Okay, so what is it? So we have this negative, let me just write it first, t1 minus t2 square plus x1 minus x2 square. So since the xi and eta coordinates don't touch the x vector, those just we don't transform, then we just need to look at this expression. So what is this? Yeah, I'm just suppressing it here. I mean, it's there, of course, in the in this, but like, for example, we could choose these A and B to have the same x vector, then this is just 0, right? So we can just take that case. Okay, so they're in the same plane. So what does this look like? This is like negative c square sinh of eta. So this eta is 0, right? So A has eta equal to 0. But yeah, so let me specialize to that. So this is c squared sinh eta square plus c square cos eta minus 1 whole squared, right? Because the c is constant on this line, on the yellow line, so let's call that c value c. And b has coordinates c comma eta, this has coordinates c comma 0. Okay, is this clear? Okay, so now what does this give us? This gives us, you just open it up, it's just c squared times 2 minus 2 cos of eta, which is just, well, 2c squared 1 minus cos of eta. Okay, so now what do we notice, right? Imagine that that strip over there was in the complex eta plane. So of course, in this Minkowski space, x0, x1, eta is real. But of course, we know that cos is periodic exactly if you went in the imaginary time direction in eta. So this correlation function has the KMS property. Property, which in particular, let me just write it, it's cos of eta is cos of I 2 pi minus eta. You can just check this. So basically, we can take beta equal to 2 pi, and we will have a correlator which exhibits this KMS property, but in this eta time. Okay. Okay, so notice that here we computed a purely Lorentzian correlator, right? I didn't make any reference to going to Euclidean space in this thing. So in principle, thermality of states can be deduced purely from Lorentzian objects just by diagnosing this kind of KMS properties. Okay, so but now let me say a bit more about why we have this thermality and so on and so forth, just to connect with things that we know. So here we have this x1 direction, and we have this R plus set. Okay, but and I told you that I hid something in here when I said it's in its vacuum state in Minkowski space. The vacuum state is defined on the whole line. Okay, so the vacuum state is defined on the whole line, but what this correlator measures is only the sensitivity of the state to the information in R plus. You see, because R plus, if you're an observer here, you cannot send a message to the observer in R minus, which is just clear from this diagram here, right? If you're a person here, you cannot send a message to this. So restricted to the set x1 positive, the state is a mixed state. Just because the global state has some entanglement between the region x1 less than 0 and x1 bigger than 0. So basically, the density matrix on R plus is exponential of negative beta times some Hamiltonian. So beta we calculated there to be negative 2 pi. And note that in the definition of g of t that I wrote, the h was the generator of t translations. So let me write this again here. G of t had some trace e to the power minus beta h e power I h t phi e to the power minus I h t phi. So H and T appear like this, which means H is the generator of translations in T. But there, we saw that the periodicity is in terms of eta, right? So this will be e to the minus 2 pi times translation operator in eta. Okay, and given the coordinate transformation I wrote between x0 and x1, this is nothing but the boost operator, or more particularly the boost operator restricted just to the right side, in restricted to the R plus. So the density matrix of the state restricted to the region R plus looks thermal with temperature 2 pi and the Hamiltonian being the boost generator. But the thing I wanted to emphasize is just the fact that one can calculate correlators and one can infer temperatures just from that. Okay, are there any questions about this? Yes. Well, no, so good point. So here you see these phi's were taken to be the same operator, but I literally meant same operator as an operator in quantum mechanics, because here I'm not exposing any x's. So if this was actually a QFT and I had a phi of x, phi of 0, then phi of 0 and phi of x are two different operators. So then I should have started with some object like A and B here. So two different operators, and they have a different KMS property. There is still some cyclicity of the trace, but it's not like you don't relate it to the same function, you relate it to some other function. So that is why I took the xi to be the same, because xi is like space. So if I set xi to be the same, then I'm just picking the same operator and then just translating in eta. Well, I just showed, I mean, it explicitly came out to be cos eta, right? And cos eta has periodicity properties. In particular, it has that property that I wrote there, like this, right? So that we should compare that to this equation here. Or this equation. Okay. Any other questions? Yes.
You said that like in a state like all operators are high KMS condition, then that will come out. Suppose if all not satisfy this KMS condition, then computer can you say something about that?
No, I don't know that.
One way.
Sorry?
This condition is one way. If they satisfy, then the state will be come out.
For all operators. Yeah, I don't know if it's interesting to ask if it's satisfied for some operators but not for others. At least I have not seen a physical situation where that arises. So.
But you showed that it's holds for all operators.
Yeah, so this thing shows that it kind of, just because of the way the kinematics is of this problem, it follows that it will, like. So here I didn't show that, but yeah. Yeah.
If you have some other state,
Yeah.
all operators do not satisfy that KMS condition. Can we say that that is thermal or not?
Well, it will probably not be exactly thermal. Like if you have a random excited state in Minkowski space, and then you restrict it to, let's say, R plus.
The theorem belongs to that if they do not satisfy that condition, then that can be. I mean, this condition only says that if they satisfy this condition, then that will be. It doesn't say that if they do not satisfy, then they
Yeah, I'm not interested in covering all cases and everything. I'm just presenting one interesting case that appears a lot and that we should know.
It's an if and only if.
Yes, it is. Yeah.
So if you find an operator that fails the KMS condition, it's definitely not a thermal.
Yes, yeah. That's true. Okay. All right, so now I want to draw some more figures, which kind of will be useful in the black hole case as well. Okay, so first of all, I should tell you what the metric looks like in these coordinates. So ds square is minus dx0 square plus dx1 square plus dx d minus 1 square. We don't touch the transverse parts at all, but it's minus okay. All right. And now we had this strip in the eta plane. So this is the eta plane, and we have this here, 0, and this is 2 pi. So let me just call the real part of eta to be eta 1, and call the imaginary part of eta to be eta 2. Then if I now choose eta to lie along this line here, then this metric on the yellow line will be xc square d eta 2 square plus dxc square plus dx vector squared, right? The minus sign goes away because eta is I times eta 2 on the yellow line. So this is nothing but a flat space in polar coordinates. Okay, and we know that when we have polar coordinates in flat space, it's the angle is periodic with period 2 pi, so that's what this is representing here. That the fact that you have periodicity in 2 pi, or the fact that the width of this strip is 2 pi. Okay, so what does this have? So let me draw a flat space in polar coordinates. So this is here, we have an origin, there is xc which goes outwards, this is the radius, and eta 2 is like this. Okay, so here is a Penrose diagram of Minkowski space, the full Minkowski space. So roughly think of this as x naught and this direction as x1. And we had these dotted lines. In the Penrose diagram, they would look like this. So the region R plus is this region, and the region R minus is this region, the complementary Rindler wedge. What I want to draw is how this disk fits into this picture. So, this is time. Roughly in this coordinate, this would be lines of eta 1, right? If I move a trajectory like this, this is the trajectory is increasing eta 1. Eta 1 was the real part of eta. So imagine now that you have a third direction coming out of the board, which represents eta 2. So eta 2 is the imaginary part, or something like eta 2. And then the point is that this disk sits like this. Or you should think of this disk as sitting like this. This point at the origin is the same point here. And if I draw a straight line, A, O, B, then the straight line A, O, B is a part of both the Euclidean section, so to speak, on the disk, and it's also part of the Lorentzian section, which we were earlier drawing. So somehow the full space part of Minkowski space, sorry, I got this backwards, x0 and x1. The full x1 line is split into two parts by this horizon. The left part is captured by the left part of this disk, and the right part is captured by the right part. So one should always imagine some pictures like this. And another set of words you can say about this is a Euclidean path integral. So if I cut out the top half, I'm preparing a state on the slice AOB. So that is this part. So there is a Euclidean path integral which prepares a state on the slice AOB. And then if I so choose, I can evolve in Minkowski time. So you have a Euclidean preparation which prepares a state, and then you evolve in Minkowski time. So from vacuum, we kind of already develop a state in Euclidean time, and then we go to the Lorentzian. Yes. Okay, are there any more questions about this? Yeah.
Looks at non-zero value of eta 1 and then imaginary eta 2.
Yeah, that it's hard to draw. Yeah. Yes.
One step backwards related to your ankle thing. So this correlator that you found that satisfies the KMS problem is true, of course, that it's periodic with period 2 pi I. But it's also periodic with period pi I. So why is the temperature not pi?
Sorry, I should have emphasized, I kept saying periodicity and I wanted to emphasize this. Notice that this condition, G of T1 was equal to G of T2 when T1 plus T2 is negative I beta. It says that G of T1 is G of negative I beta negative T1. So it's not exactly a periodicity condition because of this minus sign. So it's actually a reflection kind of a condition. So remember this midpoint thing that I was drawing, that you have to have the correlator equal when you're separated by this. So that is really the property that I'm showing by writing that equality between the two Cauchys. So think about this, G of T1 is G of negative I beta negative T1, and that's exactly that.
It's just a fact of life that I believe that this one is periodic.
But KMS is not a statement about periodicity.
This statement, this over there, delete the two. I know it's sorry, I shouldn't say periodicity, but it satisfies the KMS condition.
You mean if I delete this 2 here, this will not be correct because this side is cosh of eta plus I pi because it's even, and then it's negative cosh eta. Cosh of eta plus I pi is negative. Okay. All right, yeah, I should not say, it's like a thing that I also had to unlearn. Like this KMS condition is not a periodicity condition. It's a condition that relates these points. I mean, if you want, you could now extend this function, by just period beta. That's a separate thing you can do, is to extend this function outside of the strip by just saying that it's periodic in beta. But the KMS property holds within this strip. Okay, so
Square root of the periodicity. If you apply it twice, you get back the periodicity.
yeah, right. I guess with the 2 beta here or something. But I think the periodicity is.
If you apply it again, you get back the same.
Yeah, you get back because we can see this from this midpoint thing. Because we are just relating the value at the 2 points. So the periodicity is just by hand you declare that we have this g of t, which is an analytic function, and you can extend it periodically outside of this strip. See, from that circle picture, it's clear because at beta they will collide again, right?
You don't have a function which is not periodic, but
yeah, in principle, the function is not defined beyond that, yeah.
so you can analytically continue in principle, right? Unless
Well, the thing is, usually at these boundaries, there will be some singularities. Like typically there will be,
isolated points are everywhere.
sorry?
At isolated points are everywhere.
Sometimes it could be everywhere. So in some cases, so like if the points were like literally like this, there was no spatial separation, then the light cone singularity will start immediately at t equal to 0.
That you can analytically continue around by changing eta 1, or changing the other coordinates to avoid the light cone singularity.
No, but yeah, so the light cone singularity depends on the spatial separation. So there will be one case, if the operators in space at separation x, then you would have branch cuts here, and then you could analytically continue through here. But if the x position is the same, then this branch cut sort of extends everywhere. And then it's not possible to just analytically continue. Yeah.
You can't really extend it to outside the strip.
Yeah, in some sense, yes. But yeah, typically what happens is you get these trigonometric functions. So, but you see, even there, it's the trigonometric function raised to some power minus delta. So overall, there is still some branch cut. Okay, so now we move on from Rindler space to Schwarzschild black hole, and much of this will be just get repeated, except a very important difference. Okay, so the Schwarzschild metric is given by ds square is negative 32 m cubed over r e to the power minus r over 2m du dv plus r squared d omega 2 square. So the coordinates are u, v, theta, phi, where u times v is 1 minus r over 2m times e to the power of r over 2m. So this is an implicit relation that you should think of inverting r as a function of uv and then putting it here. Okay, so why did I start by writing it like this? Because these are the so-called Kruskal coordinates, which cover the full Penrose diagram of the Schwarzschild black hole. And looks like this. So v goes this way, u goes this way. uv equal to 0 is the horizon, and uv equals 1 is the singularity. So it's like r equals 2m, r equals 0. Okay, so notice that so these are the analogs of the Minkowski coordinates. So this, you should think of the x0, x1, and xd minus 1 that I introduced. So this is the full space-time. Now, of course, there is also the analog of the Rindler space-time coordinates, which are dr square over f plus r square d omega square, where f is 1 minus 2m over r. And these coordinates cover only this part. Okay, so we again have some situation where we have some coordinates that are covering only part of the space and some coordinates that are covering the whole space. And an observer who sits at a constant value of r, his trajectory is like this. So this is the orange person, is you should think of as the analog of the yellow lines I was drawing before. He's an observer who sits at a constant value of r. He could be close to the black hole, like this, or he could be far from the black hole, like that. But in any case, there are some trajectories. And again, note that the property of these orange lines is an observer here cannot send signals to an observer who might be on this side of the space. So once again, if you have now a field theory living on this space-time, just a scalar field, let's say, massless scalar field, and you put it in some globally well-defined state, like the Hartle-Hawking state, which we'll come to in a bit, and then you think of correlators that are calculated between points that are purely separated along this orange line. So you think of calculating a correlation function, phi of b, phi of a, where they're only separated along this line. This correlator will have the KMS property in the t coordinate, because the t coordinate is the one is like eta. So t is like eta here now. Okay, so once again, we will come to the conclusion that correlators purely measured on 1/2 of the space look thermal with a specific temperature. Sorry? Let's see how the temperature comes now. Yeah.
Hello.
Yeah.
I had a doubt regarding the Rindler coordinates.
Yeah.
In the circle where eta is the angle.
Yeah, the eta 2.
Yeah.
Yes.
That only covers the right half of the plane, right?
No, you see, because when eta 2 is pi, then you are on this left side. You can see that because of essentially what the calculation I did when Finn was asking his question. So what do we need, right? We need x1 to be negative. So x1 was cosh of eta times xi. So this is cosh of eta 1 plus I eta 2 times xi. In general is complex. So if eta 2 is pi and eta 1 is real, so cosh of eta 1 plus I pi times xi, it is negative cosh of eta 1 times xi. Xi was positive, cosh is always positive, so x1 is negative. So actually when you take the angle to be pi, you're on the other side of the Penrose diagram. So that is why, this visualizing this angle this way is nice, because you start at angle 0, you increase the angle to pi, and you can keep going like to pi. Okay, thanks for the question. Other questions? No, okay. All right, so let's see how to expose the periodicity of this again. So now again, we draw this complex T plane. Let's again, now I'm just going to call this T1, and the vertical axis I'm going to call tau. Okay, so what does the metric look like? So the metric ds square, now again we go on this Euclidean section, so on the orange line. Equals f d tau square plus dr squared over f plus r square d omega square. Okay. And now you notice that let's expand this near the horizon. Okay. Which one? The orange chalk? Okay. So we go near r equals 2m. And the property that f has at r equals 2m is that has a simple 0 at r equals 2m. So we can write this as f prime of 2m times r minus r plus d tau square plus dr square over f prime of r plus r minus r plus plus r plus square, sorry, you started using r plus 2m plus 2m square d omega square. And now you should first define a new coordinate rho such that this part equals d rho square. So that's the definition of rho, and it's easy to do because it's a simple square root. And what you will find after you do that is that there will be some coefficient here. There will be some rho square, d tau square, plus d rho square plus 2m square d omega square. And now, again, this looks like some flat space, some region which is flat. And again, this tau looks like wants to be some kind of angular coordinate. And for this space to be free of any singularities and so on and so forth, absence of conical singularities, I'm just going to write the answer that the periodicity in tau has to be f prime of 2m over 4 pi. Okay. The only difference from the previous calculation is that this coefficient was just not there in the Rindler calculation. Now, because there is this f prime floating around, that's the only quantity that's in the game. So this coefficient is something like f prime squared. So you should first define a new coordinate theta, which is that coefficient times tau, and set the periodicity to be 2 pi. So that is what gives you the beta of the black hole. Is it? Yeah, you're right. Sorry. Thank you. So you see that the derivative of f, so f vanishes at the horizon, but the derivative of f controls this beta. So again, we should put here beta, so negative minus I 4 pi or f prime of r plus. So let me draw those figures again for the Schwarzschild black hole. So this metric, f d tau square plus dr square over f plus r square d omega square. The tau and r parts can be visualized as follows. You can think of a cigar shape. So this value is r equals to m, where f vanishes and this circle smoothly shrinks. R increases this way. This is r equals infinity. And at r equals infinity, the circle doesn't keep growing bigger and bigger and bigger because f approaches 1 as r goes to infinity. So the size of this tau, is beta asymptotically. It doesn't keep growing. Unlike here, here it keeps growing forever. So the basic point of the Schwarzschild black hole is that this function, which multiplies the eta 2, interpolates between a quadratic behavior near this tip to a constant behavior at infinity. Whereas in Rindler space is just quadratic all the way, c squared all the way. Okay, so this is what we can draw. So again, let's cut it in half, like we did it here. So you cut it in half. So you will get some slice like this. So we can call this A, O, and B. And we have this Penrose diagram of the Schwarzschild black hole. You can draw these horizons. So topologically, this is still a disk. Even though I've drawn it like this, it's clear that I can deform it. At least its shape looks like a disk. So we have A here, O here, and B here. And we have this time slice. And this cigar, again, fits in this direction. So that's like this yellow line. Okay, so once again, we can say the same words. Imagine this T to have an imaginary part, which is coming out of the board. And you have this disk sitting here. If you only consider the path integral on a half disk, this would prepare a state on the slice AOB, which is a global slice in this diagram. It will prepare the so-called Hartle-Hawking state, and then you could evolve it in time. And it also tells us that if we trace out the part AO, the state of the quantum fields on OB will be thermal with that temperature beta that we calculated. Sorry, which one? The upper one is just a disk, right? So let me smoosh this into just a disk like this. So topologically, this is the same. If I don't care about representing distances faithfully, then this is just AOB, right? This is the same. Like just imagine bringing this and like flattening it. Okay, so again, we see that the Euclidean part of the geometry knows about the other side. If you went in T by half of beta, you would end up on the left side of the black hole. Okay, so now one more very important difference from the Rindler space case is that we had this dx vector square flying around in the Rindler case, like it was infinite in the transverse direction. Whereas here, the transverse space is finite, it's a sphere. It's not some infinite direction. Okay, so that is also an important difference to keep in mind. Okay, so, now I will make some, just some remarks. So one thing is we've been focusing on calculating is there a question? So we've been focusing on trying to calculate 2-point functions and show the thermality of these states. But also one should be able to calculate, let's say, just the 1-point function of the stress tensor. If I want to consider an evaporating black hole, oh yes.
I know of a computation and it's very common when you can do a Parrikar explicitly to get the vacuum states wave function.
Yes.
In this case, could you do this for Gaussian black hole? Doing this on a semi.
Well, I mean, in some sense, yes. I mean, what will you do? You will do some mode decomposition of your scalar field. You will just say that you have some creation and annihilation operators for those modes, and you will just set them up in the right state, like maybe I'm not sure I'm understanding your question. So, yeah. Yeah, so I mean, I didn't do all this because I don't have the time, but typically you put a scalar field, you solve the Klein-Gordon equation, you get a complete set of modes, and you get some creation and annihilation operators, and that's the way you go.
Yeah, that's the way I would proceed in the Rindler case. But in this case, there's an additional aspect that this is supposed to have some gravity.
No. So no, we are just doing QFT on a fixed background. There is no gravitation turned on here. So if you want, the Newton's constant right now is 0. So you're just doing purely scalar field on this geometry. Yeah. Yeah. Sorry? Cylinder of length. Well, the point is, now we are not doing QFT on flat space, right? We are doing QFT on this manifold. So we have to set up the thing appropriately for this manifold. So sorry? In which cylinder are you talking about? Sorry, maybe I'm not getting your cylinder. Where's the cylinder here? Of a QFT? Yeah, but that will set up like some thermal state on some infinite straight line, right? If this is the infinite side of the cylinder and you do some beta, but I'm not talking about some line, right? I'm talking about this particular manifold. Okay, so in this paper, actually the first paper, calculates, for example, the expectation values of stress tensors. And some of these other papers, like this paper, refers to a lot of papers that calculated the 1-point function of the stress tensor in the Schwarzschild geometry in some approximations, and including some semi-analytic formulas and so on and so forth. The point is, stress tensor is like quadratic in the field, like it's typically d mu phi, d nu phi. So it's still like a 2-point function, but you have to take a coincident point limit and subtract out some divergences and things like that. But there are enough references here that you can look that up. Okay, so now we come to this fact about this finiteness of the transverse area. So yes, please.
I mean, had we gone to the same trouble to calculate the stress tensor in the Rindler case, we would have gotten 0. But it would have seemed like some kind of weird coincidence, right?
No, so there's 2 stress tensors in the Rindler case you can calculate. One is like in the Minkowski vacuum, and one is in the Rindler vacuum. So that one will show, those will not be equal.
Right, but in the Minkowski, the one where we did the 2-point function,
yeah,
the Minkowski vacuum.
Yeah, that will give you will give you 0. But now let's say we want to really see, so somehow we must feel that a thermal state should have a higher energy than the vacuum state. But it's a thermal state with respect to the Rindler Hamiltonian. So we should compare that energy to the ground state energy of the Rindler Hamiltonian, and that actually works out to be negative. So the Rindler ground state Hamiltonian has a negative energy, and then the Minkowski vacuum is like an excited state on top of that. But of course, that state is singular on the horizon. So that's why you don't consider it when you're doing global QFT. But okay, so the finiteness of this transverse size comes in because now we are going to assume, for the purpose of this lecture, that there is a Bekenstein-Hawking entropy which is given by area of the horizon over 4G. So in the Rindler space case, this is just infinite, but for a Schwarzschild black hole, it is finite. Okay, and now we are supposed to imagine that this was not a flat space black hole, just for concreteness. Imagine it was an ADS black hole. It was an ADS black hole that had positive specific heat and all those kind of things. Then we believe that there is some non-gravitational description of the system, some non-gravitational system, such that the entropy of this system at temperature beta equals area of the horizon over 4G. In particular, it's finite entropy. So the black hole in the dual system will represent a thermal state of just a non-gravitational system with this finite amount of entropy. Okay, so let me draw for you the Penrose diagram of an ADS black hole. It looks like this. It doesn't go like that. And now we have a problem already. There is already a contradiction because imagine this Hamiltonian here, which was evolving you in Schwarzschild time. So imagine the killing vector partial t. And there's an operator which evolves quantum fields in time t. On the one hand, we expect it to become the Hamiltonian of this boundary system. So it should have a discrete spectrum. On the other hand, the same operator acts like boosts near the horizon. And you can show pretty generally that a spectrum of a boost operator is always continuous. You can see it from the wave equation, you can see it from more abstract arguments. So that already presents a contradiction. The fact that there is one vector field which is acting like a boost near the horizon and a time translation near infinity. And we believe that this time translation is the Hamiltonian of the dual quantum system. So this can be called people usually call it the Maldacena version of the information problem, it was not discussed exactly in this language, but basically this in the paper called Eternal Black Holes in Anti-de Sitter. So there you calculate some 2-point function and so on and so forth. But the point is, because of the boost operator having a continuous spectrum, because it acts like a boost, the 2-point function calculated using the bulk geometry will decay in time exponentially. So I didn't give that reference. I should also give that reference. So I did. Seems like I didn't. Oh no, it's here. Okay, so this is one version of the information problem which is present even in an eternal black hole. Yes. Well, we can look at this, for example, this formula here. So, okay, in ADS it's slightly different, but f approaches 1 near infinity. So basically the time translation is just like, sorry? Yeah. Yeah, but it is a deep fact that spectra of operators that look like boosts is always continuous. Yes.
Really follow why this is a version of a paradox.
Well, you may not call it an information paradox, but it's a paradox. It's a paradox because you have one operator which is generating translations in time. From one point of view, it has a continuous spectrum. And from another point of view, it has a discrete spectrum. If you believe that this operator is the time translation operator of this system. Like in ADS-CFT, you believe that, right? You believe that translations near the boundary are the translations of the dual quantum mechanical system.
Is that guaranteed?
It's not guaranteed, but if you believe in this logic, which for ADS-CFT is probably definitely true, then you have a contradiction. Okay, so the next topic is going to be collapsing black holes and black holes that actually form from collapse and things like that. So are there any questions about this? Yes.
I missed, why continuous spectrum? Could you just one second?
Well, I haven't not explained that, so I'm asking you to take that on faith for now. One quick way to see it is that anytime you write a wave equation for, let's say, a scalar field moving on this part, and you go to this tortoise coordinate, the potential always go to 0 as r star goes to minus infinity. So essentially, there's a flat, almost flat direction in the potential. So there's like a continuous number of states. In ADS, that potential is like 0, and then infinity like rises to like r square at infinity. But on the horizon side, it's flat. So that's one way to see it.
I guess it's not a sharp contradiction because that statement was about quantum field theory.
Yes, so exactly. So the way out of this paradox is that exactly like Matt is saying, this statement is a deeply quantum gravitational statement, whereas the statement about this operator acting like a boost near the horizon is a statement that you make using QFT on this fixed background. So clearly, the quantum gravity wave function, whatever it is, will have support on different geometries. So then, this bulk is fluctuating in quantum gravity. It's never a fixed geometry. So those are the kind of things that come in to help you at least partially resolve this paradox. So for example, in this paper of Phil Saad that followed the SSS paper, he showed how to get a non-decaying contribution from things like wormholes, the space-time wormholes in this same kind of setup. So. Okay, more questions?
Would one be very naive and say that what this means that the classical approximation breaks down?
Yes, it breaks down if you ask the question that will make it break down, it will break down. Yes, like that's like those are very sensitive questions about because the spectrum here, even though it's not continuous, it's discrete, but the amount of discreteness is like very small, right? It's e to the minus s, where s is very big. So for all intents and purposes, it looks continuous if you don't look too closely. But yeah. Yeah, I think that is not really the issue here. The issue here is really about the spectrum of the underlying operator. Because we didn't really start with any pure state or anything here. So, like even in a thermal state of a normal quantum system which has a finite entropy, it will decay for some time, but eventually there will be recurrences and things like that. So it's a question about that. Okay, so now we come to collapsing black holes, and I have well, it's not no one has figured out a complete resolution yet, which is why these problems are still interesting. But you can ask, there are, so what would be the setup? The setup would be, you would set the problem up on the boundary like always in gravity. Let's say you want to calculate some 2-point function. You will set up the asymptotic boundary conditions for the 2-point functions, and then ask, what geometries can I fill into these boundary conditions? So one geometry is this kind of Hartle-Hawking geometry, is this disk geometry. And you get some results from that geometry. But plus you could have, for example, these space-time wormholes, which are suppressed for some reason, but might be enhanced for some other reason. And so it could be suppressed by e to the power of minus s, but it could be enhanced by something growing linearly in time. So then if you go to late enough times, that contribution becomes important, things like that. So you would have to sort of sum up contributions which in the bulk don't have this geometry at all. Like the horizon will not even be there in those geometries. Okay. But that's the essence of all kind of paradoxes. Like every time you look under the hood, you will find something which you're making some kind of semi-classical approximation. Yeah. Yes, yes. N is large but finite. Like because see, G is related to N. If G was 0, this would be infinite. So this is order N square, right? So to have finite entropy, you need to have finite N. Okay, so let's maybe go to collapsing black holes, which I really refer you to this paper. It's not maybe the easiest paper to read, but I think it's worth it trying to wreck your brain with these 10 pages. But it's very nice. Okay, so we have some collapsing black hole, a star which collapses to form a black hole, and we want to investigate, because that was Hawking's original setup, and we want to understand what they were talking about. So the first order of business is to define the right coordinates. So we have this ds square is minus f dt square plus dr square over f. We first define a coordinate, this tortoise coordinate, dr star, which is dr over f, and that is equal to negative f negative dt square minus, actually let me not write the metrics. Okay, so then you define a v, which is t plus r star, and a u, which is t minus r star. But I also want to define a tau, which is, this tau is now no longer the imaginary part of t, forget about that discussion. Tau is v minus r. So we will work with the coordinate tau r theta phi instead of this t. The point is that in this Penrose diagram, these coordinates are smooth across this horizon. So I'm using this v coordinate, or instead the tau coordinate. I can go behind this future horizon. So let me draw a picture of what these coordinates look like. So this is r, this is tau. I have a star which collapses to form a black hole. This is the collapsing star, and at some point the star crosses its event horizon. So this is r equals 2m. Okay, and I will define this line where it crosses the horizon to be tau equal to 0. Okay, so this part is the interior of the black hole region. And in this, we have the property that light rays that go to the left are just 45-degree lines. They are given by this v equals constant. So if v is constant, and we can see that that is a light ray from just this equation, then that's just this. Okay. So these light rays, we don't really care about that much. But we care about the opposite light rays, which are trying to make it out. So if you're very far away, you just go out, no problem. But if you're close to the horizon, these light rays have a very hard time making it out because the gravity is very strong. So you have some picture like this where it like hugs the horizon for a long time and then eventually makes it out. And if you're at the horizon, it never makes it out. Then on the other side, they just fall into the singularity. Okay, so this is the structure of the space and the causal structure. Thus is u equals to constant. So here the symmetric can be written as negative f du dv. So plus I'm started dropping the angular part, but so one light ray is v equals constant, the other one is u equals constant, but we didn't draw the u coordinate. We draw this coordinate because otherwise you won't cover the region behind the horizon. Okay, so it's also useful to draw the Penrose diagram. So the Penrose diagram now looks like this, actually. So despite looks like there is only one asymptotic region here, I'm just drawing it like this. So this line is like r equals 0. This is r equals 2m, and you have some shell that formed in and formed the black hole. So you should really think of this part as being on top of it. Or in other words, each point on this Penrose diagram is half of a sphere. So this point here has half of the sphere, and this point has the other half of the sphere. Okay, so this is the Penrose diagram, what it looks like. The biggest difference from this, of course, is that there is no past singularity, and there are no past horizons. So what does this rough? All right, this is the exterior metric, of course, thanks. And inside it'll be something else, but the inside metric will not be important for the calculation, and so on and so forth. Yeah. Okay, so what is now, how do you think about this? Because now, as Matt was saying, this is not really the full metric. The full metric clearly does not have time translation invariance in the full sense of the word. So it's not as simple as the previous cases, but we still need to somehow, we know that there are some thermal effects in this geometry, and we need to sort of uncover them. Okay. So again, we imagine some observer here. He's outside. He's very far from the black hole. He's just sitting. And again, he's measuring 2-point functions. So he again wants to measure some 2-point functions and wants to see, what does the 2-point function look like as a function of t. So now, of course, we should say some words that this observer should be far away from the black hole. He should wait enough time so that all the transients from the collapse have gone away. The black hole has settled down, and after that, he starts measuring these 2-point functions. Okay. So now I won't have time to present all the details, but the idea is the following, that this 2-point function, in some limit, is going to be controlled by an light rays that come from here. So you can back translate this 2-point function because you're at late enough times. And so what this paper shows is that at late enough times, this 2-point function is controlled by a limit of the 2-point functions here. So let's first see how the light rays behave in this. Okay, so the outgoing light rays have U, which equals T minus R star, is constant on the light ray. Okay, and well, this you can just check that it's also equal to tau plus R minus 2R star. Well, that's clear because tau was V minus R and V is T plus R star, so these two expressions are equal. So let me just draw that same picture here. So we have this singularity, we have this horizon, we have this star crossing the horizon, and we have this, this light ray going out. So imagine a light ray that comes out at very, 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 very late times. By this logic, it must have started very close to the horizon. Okay, so we are going to put this quantity constant between this point A and the point B, which is very far away. So when you are very far away, it is better to use the expression just t minus r. Okay, so that's for point B. Why? Because I didn't write the expression for it before, but let me write it now. R star is r plus 2m log of r over 2m minus 1. So when r is very big at point B, this logarithmic correction is not important compared to this. So this is the value of u at point B, just t, and this is approximately r when r is very big. However, on the point A, r is very close to 2m. So it's this log which is more important. So when we write this, and the t coordinate is breaking down, so we should really use this expression on the thing. So that's tau. So tau here was 0. So it's 0 plus r. R is approximately 2m. Let's say it's 2m plus epsilon minus 2 times r star, right? Minus 2 times this r star. R star again has some 2m plus epsilon plus 2m times log of epsilon over 2m, right? So this thing, the left-hand side expression is for point A. So point A and point B are on the same light ray, and we have just written the equation of the light ray. So what does this tell us? So note this R was capital R for the point far away. So T minus capital R equals negative 2m plus epsilon minus 4m log of epsilon over 2m. Okay, so now epsilon is very small. So essentially we can ignore these things compared to epsilon because log of 1 over epsilon is going to be very big. So essentially what that tells you is that T minus R is approximately equal to negative 4m log of epsilon over 2m, which means that epsilon is roughly e to the minus t over 4m times some e to the r over 4m times 2m. Okay. So what does this say? This says that if you want to wait for longer and longer time, so t gets bigger and bigger, the epsilon should get smaller and smaller with this dependence in time. Okay. And there's an exponential here. So if you want the light ray to come out very late, you should start exponentially close to the horizon. So there's an infinite number of light rays here, which make it out later and later and later and later and so on. But the relation between epsilon, which is the, roughly speaking, the proper distance here, there is no funny metric factor in these coordinates, which is why we went to the tau and r coordinates, it's just exponential. Okay, so now we use the following fact. The fact that this person here, who is measuring these 2-point functions, okay, he's interested in measuring the 2-point functions between, let's say, the point B and B prime. He, and I refer you to the details to the paper, this 2-point function will be controlled by a limit of a correlation function between A and A prime. You just back translate the light rays. But now both A and A prime are very close to the horizon, which means they are both very close to each other. And if the state is smooth across the horizon, those 2-point functions have a universal form. Basically, if it's a free field in 4 dimensions, it will have the 2-point functions will be 1 over the distance squared. Distance measured in terms of epsilon. So then you see again this exponential is appearing. So all your correlator again, the dependence on time will have this exponential form, which again has some periodicity in time, right? There's an exponential, so it will have a periodicity in time, which is 2 pi I times 4m, which is 8 pi im, which is the temperature of the black hole. So essentially by thinking of the 2-point function as like, the late time 2-point function as essentially being controlled by a UV limit of a correlation function near the horizon, you get a universal answer. Okay, so that reflects the thermality of a collapsing black hole, but why does it evaporate? Like the eternal black hole also had some thermal properties, but it didn't evaporate. The answer simply has to do with the fact that here you had a past horizon. So the state, even on the past state, is thermal. So you have some thermal incoming flux and thermal outgoing flux which balance. Whereas in this collapsing case, this state is just vacuum, there is nothing going in. So that's why the black hole shrinks when you don't have this past singularity. You see this scry almost got interrupted by the singularity. So if we look at the state here, the state on this scry minus will look thermal, which means there's a thermal injection of particles into this diagram, but not into that diagram. Okay, so the formal way to calculate it is you have to calculate, as I was saying, the stress tensor, the T mu nu in this geometry, in particular the flux component, the TTR. So let me just finish. You have to calculate the TTR component, which represents the flux. The diagonal components of the stress tensor are just densities which sit there, but this off-diagonal component represents how much stuff is leaking. And roughly you try to solve this equation, R mu nu minus 1/2 R G mu nu equal to this. And I refer you to the details for the 2D case to this paper and for the 4D case to this paper. And so the black hole will evaporate. Okay, we are out of time. I haven't told you what exactly the paradox is here, but maybe we'll get to it next time, and let's stop for questions. Thank you.
So versus the usual Bogoliubov coefficient calculation of Hawking radiation, the advantage now is we didn't actually need to assume it's a free field? Or did we actually assume it's a free field?
This derivation, I think, still, at least the derivation I know of in the paper, still assumes that it's a free field.
But was that just at the last step of getting
so let me think one sec. Yeah. Sorry. You're right. No, it does not assume the free field. Yes.
But it just did. In the UV, it's. Yes. I mean, you don't even need to assume it's. You would still get that it's thermal, even if it was some strongly coupled fixed point, right?
Yes. Yeah. No, but I think as long as it's a power law, you will get the right behavior, right?
Right, it wouldn't be.
Yeah, it wouldn't be particles, but this correlator as a function of t will have this imaginary time periodicity. Yeah. Sorry, in this paper, they do use the Klein-Gordon equation, which is the reason I was getting confused. But they use the Klein-Gordon equation just for the support functions of some detector.
Oh,
so there is a detector which is localized far along the orange line, and it has a smearing function. But that when it gets smeared next to a scalar, you need to back evolve that smearing function to see where it was coming from. The Klein-Gordon equation was used just for the smearing function part.
The key assumption or the key observation is that the horizon is smooth?
Yeah. Well, yeah, in this calculation, we had to assume the horizon is smooth because we are approaching this, right? And if, for example, the state was singular on the horizon, like the stress tensor was infinite there or something, then you would not be so sure that the singularity, the short distance singularity, is still a power law. Yes?
So I didn't quite follow your argument after you tried to say that this 2-point function on the orange line this can be computed 2-point function
on the horizontal line. With the A and A prime being very close to each other. Yes.
Right. Okay. If I accept that, then you try to say there's a thermality that follows, and after that you said that the black hole is evaporating. So the black hole evaporating, as you can see from the diagram.
Yeah.
That there's no incoming.
Yes.
But what is this connection with thermality now?
Well, the connection with thermality is that, first of all, people would make the statement that even if you have a black hole that formed from collapse, it still emits Hawking radiation at some temperature. So you still need to calculate that temperature. And this thermality calculation is showing you what the temperature of that Hawking radiation will be via this 2-point function calculation. Right? I mean, the Hawking radiation has some temperature. So this is the
Connection to KMS again.
yeah, via the connection to KMS, because that epsilon is related to T and there's an exponential here. So everything, if you shift T by 8 pi Im, right, you get things that are, you should,
Carrying out this kind of calculation.
yes. Yeah. Other questions?
So if I recall correctly, with the Hawking's original calculation, there is sort of some slightly dodgy assumption because these modes were super Planckian at the time when you had to assume they were in their ground state and all of that kind of thing. So does this avoid that, or are we still making an assumption about sub-Planckian distances?
I think we don't, because all we are assuming here is that the state on this slice here is just some smooth state that's across the horizon. So I don't need to refer to any times extrapolating to Scri minus or something. So if I believe that at this time, which is like sits in the middle of the Penrose diagram here, right? All I'm saying is that the state here is just nice and smooth. So then I don't need to talk about. Yeah. Well, capital R, I think should be large, like, because I haven't told you all the steps. You have to look at this paper and see the, you have to still sit far away from the. Well, okay, maybe let me not explain it, because I didn't really use that formalism. So let me just say that if you calculate this stress tensor, this TTR component, if you look at the papers, they will calculate these things for you, and you will see that there is some outgoing flux of particles near Scri plus. It's very simple in the 2D models. You just have to use the trace anomaly and some conservation equations, and you get some, like it's the so-called CGHS model. You could study it. There it's very explicit. Yeah.
Yeah, hi. Is there a slightly more invariant way of saying this entire thing, that the fact that the state is really supposed to be regular at the horizon?
Okay.
In the case of Rindler, it's supposed to be regular at the Rindler horizon, like the global vacuum of the full Minkowski space, which accelerating observer will measure some KMS type condition to deduce that it's a thermal state for accelerating observer. In this case also, it's slightly like an constant accelerating observer because it's at fixed R.
Yes.
But like removing this aspect of fixed R observers, if I have a generic observer moving in the exterior of the black hole, is there a slightly more invariant way of saying this entire thing? Because they won't see quite a thermal radiation, because thermal radiation is specific to fixed R observers. Because KMS is true for fixed R observers.
Yeah.
But I mean, some analogous statement should be there, right? Because we still want to attribute thermality to the black hole, even in an invariant fashion, I would say.
Yeah, so I guess maybe I'm now just speculating, like one observer is the one observer at Scri plus, right? Because that's given to you in this Penrose diagram. So what the observer at constant R at large is doing is basically sort of mimicking this Scri plus. So maybe what you need is some notion of a state on, like, what the observer on Scri plus is really seeing, because that's an invariant object in this conformal diagram. But I don't know about.
No, I'm trying to ask the opposite question. If I give you the observer moving on some time like
if the observer is like some crazy thing, right?
Not quite a fixed R observer, because fixed R would require constant acceleration.
But I think those, maybe you would have extra effects based on the acceleration of the observer himself. So those effects would sort of contaminate the stuff which is coming from the black hole versus, what the observer himself is seeing, because he himself is moving so violently or something. And that latter effect is maybe not so interesting from the black hole's point of view.
I agree.
So that's why I was saying that there's some natural anchors at infinity with which respect to which we are seeing this. Right? Because the notion of empty is defined for those observers, or roughly. Yeah.
Can you elaborate on the idea of the smooth
Okay. So, well, first notion of smoothness is just that none of the geometric invariants are getting big there. So Ricci scalar squared, Riemann tensor squared are all smooth. So it's a smooth, like small curvature space. And essentially what we want to say is that if I construct a state of quantum fields on this slice, which goes through that point, then none of the 1-point functions of the field should also be very drastically different at this point. That's what it means, that the 1-point function as a function of this coordinate that goes across the horizon is like a nice function.
It's this 2-point singularity that's very important, right? Because if that doesn't come out right, then the stress tensor will diverge, because in renormalizing the stress tensor, you remove that. And if it diverges, then the Ricci, some curvature invariant will diverge by back reaction. So, 2-point function, I think I would say is
having the right UV structure is really important for this. Thank you.